In this lecture, we'll start talking about some of the debug environments that exist, really a couple of debug environments that are commonly used. Our Arduino won't give us access to these environments, but it's sort of important for making IoT devices in general that you understand some of these debug environments, because if you're going to make some bigger ones, you're going to use some of these. So remote debugger, this is a common type of environment. You can see there are basically two components. There's a host computer up there. There's a target. The target is the target platform that we're dealing with. So in our case, that would be the Arduino or whatever board, Raspberry Pi, whatever board we want to work with. So the host computer is where you as a user, as a programmer, actually interface with the debugging environment. So you are typing debug commands into the host. Those are getting transmitted to the target over some kind of communication link. So the front end is running on the host that you, the programmer, are accessing. Now there's a debug monitor, some code, hidden on the target. I say hidden like a bootloader, okay? It's on the target. So there'd have to be code running, a debug monitor code that's running on the platform, on the Arduino, let's say. So it's typically triggered when some debug event occurs. So debug event, there are a lot of possible debug events. One debug event is a breakpoint, let's say. You set a breakpoint, say at the host, you said, okay, break on line 23. You select that. And then you run the code, and when line 23 happens, the target stops. It recognizes the debug event, it stops, and then it stops the running, and then it goes back to the host unless the host have control again. So that's a typical debug event. Often the host program, the front end, will have some kind of a way you can force a debug event. You hit Control-C, let's say, into the or click on a button, a stop button in a GUI built on the host, and then that sends a command to the target to stop execution at that point. So you've got a debug monitor, and the debug monitor is the code running on the target that's talking to the host. Okay, so there's a communication going on between the target and the host, and that communication has to be managed by some code running on the target. So that code running on the target is the debug monitor, and it will stop execution of the code on the target. It will monitor the communication link to see commands from the host. It'll also provide debug information to the host. So for instance, if at the host you type print the contents of variable X, that command will be sent over the communication interface, and then the debug monitor will receive it, will retrieve the value of X, and send it back over the communication link. So the host front end is actually talking to this debug monitor, which is running on your Arduino, but it's along with whatever the actual code is, the functional code, the application code. There's a debug monitor running in the background. Hitting a breakpoint, receiving a request from the host, these are the type of things that are debug events that typically cause the execution of the target to stop and cause allow interaction with the host. And the monitor maintains the communication link. The monitor and the host together maintain that link. So advantages of this type of setup. So you get good run control. You can set breakpoints to stop execution when you want to. You can actually force execution to stop from the host. You hit a button and it'll send a command to stop execution. So you get good run control. The monitor can alter memory and registers. Right, so the debug monitor is code that's running on the Arduino. Since it's running on the Arduino, it has direct access to the registers and the memory on the Arduino. So now, with a debug monitor, you can actually control the registers. You have controllability of the registers and the memory on the Arduino, and also you can read it. You have observability of those too. Perfect functional accuracy. So by that I mean that the code, when it executes, will run exactly the way it would on a real target platform because it is running on a real target platform. So you get perfect functional accuracy. Unlike, say, you had a simulator or something like that, you don't have to worry about functional accuracy. Disadvantages. So these debug interrupts, these debug events that allow interaction with the host, those things alter the timing. They mess with the timing. They stop the execution of the target, altering the timing. And so you can't get real-time monitoring using a system like this. So depending on how important timing is to you, this may or may not work. This may or may not be sufficient. Now, even for timing-critical systems, using a remote debug setup is a good idea at first, but eventually you need to test the timing too, so this type of setup wouldn't be as useful. And you need a spare communication channel. So the host and the target are speaking over some communication channel, so you need an extra communication channel, one that's not being used functionally. So if the application is already using the Ethernet, right, the program's using it for whatever the application is, then you can't use, not that you can't, but you have a difficult time using the Ethernet also for debugging. Now, it turns out you can share the Ethernet for both. But if you do that, then whenever the debugging information is going over the Ethernet connection, then functional data can't be going over the Ethernet connection, right? So there's a trade-off, and it can slow the machine down and so on. So you need some spare connection, which we fortunately have with an Arduino. UART, serial connection, is what we're going to use, and we'll talk about that later. Oh, another thing is that you would like to have the program in RAM in order to add the breakpoints. So this has to do with how software breakpoints are added. Now, you know, in an Arduino, the program is generally in flash. It's resident in flash and executed out of the flash memory. But you would like to have it in RAM because flash is slow to reprogram and RAM is fast. So if you can reprogram flash, but it takes a long time. You have to, relatively long time. When I say long time, I mean it's milliseconds, okay? A long time, lots of milliseconds. That's slow. So you would like it to be in RAM because whenever you set a breakpoint, and I don't want to go into the details of this, but when you set a breakpoint, you have to alter the code temporarily. You go to the place, the line of the code where the breakpoint's going to be, and you change that instruction to something else temporarily in order to stop the code at that point. And so you need to be able to change the code relatively quickly in order to set these breakpoints, and Flash makes that harder. Okay, so another way to go, which is more common in modern processors, is become common, is the use of an embedded debug interface. So what this is, you see this in modern processors nowadays, you have embedded debug logic, debug logic that's actually built into the processor. So inside the processor or the microcontroller, in addition to all the logic that actually executes the code, they put debug logic, hardware that actually does debug activities. They build it right in. So you don't have to have a debug monitor anymore, right? The debug monitor was a program that runs on your Arduino, let's say. This is saying, look, forget the program. We're going to put hardware in there that does those functions directly, which makes it faster. Also makes it possible to do in parallel. It's efficient. It costs a little bit because it costs area on the chip, right? The chip has to get bigger to accommodate the extra logic that you're embedding in there. But it's a useful feature, and it's getting more and more common because space is relatively cheap on a chip. So typically it's an optional IP block, intellectual property block, optional piece of hardware that you can add to the chip design. There are several embedded trace macrocell from ARM. So ARM processors, they have embedded trace macrocell, which is the name for their debug logic or for some part of their debug logic. They have several trace macrocells, but embedded trace macrocell is the main one. Freescale uses background debug mode, which is a similar idea. Debug logic is permanently built into the processor. So what that means is that logic, since it's debug logic, generally it's used when you're developing the system, but once you manufacture the system and you sell it, that logic it seems wasted. It's not being used, right? Because you're not generally debugging it out in the field. Now, you could, but that is much less common. So that logic, this is why somehow it seems like a waste sometimes, because you say, well, I'm using that logic, I'm paying more to build this chip with this extra debug logic, but in the field it's never used. That's true. It's not a waste, though, because debug costs a lot of money, and anything that can speed that and make that cheaper is not a waste. A few dedicated pins have to be added. So this debug information that is extracted by this embedded debug logic, it has to be sent to, say, a host machine, right, that the user is interfacing with, is using. So in order to do that, you need some pins to send that data. And that's important. The pins are precious, right? There aren't that many pins on a chip. Even a very densely packed chip has a lot of pins. Compared to the amount of logic inside the chip, there are very few pins. So pins are precious. So you don't want to use too many pins just for debugging purposes. But these debug interfaces require a certain number of pins. Usually they transfer data serially, so they need very few pins. But they do need a few pins dedicated to debug. So here are some of the debug and trace features you would expect to find in embedded debug logic. Breakpoints, the ability to set breakpoints inside your code. Watch points, where what happens is it's sort of like a breakpoint. It's at a certain point in code, let's say, or on a memory location. If some event happens, then it stops the code. So maybe if you write to a particular memory location, then it stops it. So every time you write, it'll check, and if you write to this location, then it stops the code. On-the-fly memory access, so you can access the memory locations at runtime without stopping the code. You can observe the memory locations. You can read them and observe them. You can change processor values, so change register values and things like this. Single step through the code, so one step at a time, one instruction at a time, which allows you to, it's basically fine-grained run control. So you execute one instruction, you check the value. Execute the next instruction, check the value. And you can zero in on exactly when the value is going wrong. You can export exceptions to debugger. So when you hit a watch point, it can go to debugger logic and start running debug logic if you want it to. You can export software-generated data. So what that means is actually we're going to be doing this. We will actually be doing something just like this. You can basically allow that the person who writes the code running on your target, they can put print statements, effectively print statements, which send data from the processor to the host. So you can basically add error messages manually. You can say, oh, this error has happened now, and it'll be sent on the wires, whatever the communication interface is. It'll be sent to the host, and the person debugging can see the messages, and that can be helpful. Time step information for each event, so you can trace the events. So when events happen, like certain interesting things happen, a memory access happens or something like that, you can send a timestamp and say, look, this memory access happened at this time, this happened at that time. Sometimes in time and critical situations, time and critical systems, you want to know exactly when things happened and the time separation between events. So the hardware that you add for debug can add that timestamp and send it to the host. An instruction trace. You can have special purpose hardware that tells you which instructions are executed in what sequence. So this is very useful sometimes. If you want to know, something crashed, you want to see what happened that led up to that crash. You'd like to see a trace, the list of instructions that were executed, so you can follow it back and sort of guess at which instruction or which set of instructions might have caused that crash. Thank you.